Newton's method. Very easy approach. Nothing too complicated here. It's based off of the concept of a tangent line. And in fact, the Newton's method formula is derived from the tangent line equation. This is what we call an iterative process. I gave you a program in your calculator. It's called Newt. That'll do Newton's method for you. The problem, as with every other topic that we cover, is that you could have all these calculator resources and they're wonderful. If it's on the non-calculator part of the assessment, then what? You know, you still got to know how to do it by hand. So an iterative process, what does that mean? It's talking about the idea that if you have a formula and perform a substitution on that formula, so substitute a particular value, do a little plugging and chugging, you get an answer from that formula, take that answer, pop it back into the formula, and run a new set of calculations so that you can get another result, which you would then plug back into the original formula, do some plugging and chugging, and get another result, plug that back into the formula, and stop either when the directions tell you to stop or when it makes sense to stop. And you'll see in a few minutes when it makes sense to stop doing something. All right, so what Newton's method does is it gets us the zeros of a function, and with a slight bit of manipulation, you could actually get the intersection between two functions. When you use the intersect feature on your calculator, it's applying Newton's method, right? So it's actually always been doing that. The solver does it too. That's been its underlying programming, which is kind of cool to think about. All right, so our equation of a tangent line, you know, if we're given a slope and a point, slope in a calculus sense is the derivative at a particular point, all right? And that point would be, we're going to denote it as x of n, comma f of x of n, all right? So x comma y, where y is a function of x, all right? So if I were to pop that into my point slope form, whatever variation of it, I would get this guy right here. Slight manipulation. Let y equal 0, because again, if we're looking for roots, that's what would happen. That's on the x-axis. With a slight bit of manipulation of this formula, replacing the y with 0 and solving for x, you would get this relationship, and this is what we call Newton's method. All right? So what this is a resulting x value based on a prior x value. All right? It's a recursive model. So anything that calls back upon something that was a prior calculation is what we call a recursive model. All right? Any operation on a recursive model is called an iteration. All right? So the way we define Newton's method is to say that we're going to start off with some value of x, whether it's the first value, the second value, whatever. And what we'll get is the next x value in the process, in the iterative process. All right. So the key to this, and you'll see this in action in a second, very tedious if you have to do it by hand. When I show you how to do it on the calculator, like, this is not so bad. All right. It's number 3 that makes it a little crunchy, because if your calculation is within the desired accuracy, then you can stop. But it's like, how do you know what the desired accuracy is? All right, is it what you desire it to be, or what someone else desires it to be? So that's the thing, and we'll talk about that in a few minutes. All right, so we'll tackle a problem. We're going to calculate 3 iterations of Newton's method to approximate a 0 of this model. Actually, let me. I'll take it as a typo. Include formula, for example, one on page whatever this is. All right, so you notice the ingredients. We have an f of, and then we have an f prime of. All right, so f of x sub n. Well, what's x sub n? Well, let's start off with the fact that they gave us x sub 1. All right, if that's the case, then what we're looking at here is x sub 1 plus 1, or x sub 2, is equal to x sub 1 minus f of x sub 1 over f prime of x sub 1. All right, because, again, that subscript, if we're just matching it up based on the model, that subscript would have to be the end value. All right, so what I need to do is evaluate the original function and also the derivative. So I need the derivative. In this case, not too bad, just a 2x. All right, so x sub 2 is unknown. That's what we're looking for. X sub 1 is 1 minus, so then we would plug the 1 into the original function, and that would give us a negative 1. And then plug the 1 into the derivative, which is going to give us a 2. So it would be 1 plus a half, which would be 3 halves. All right. So we were given our first x value. This is our second x value, but this is actually our first iteration. All right. So the first run through the calculations, this is our first iteration. The second iteration, all right, that would be, because now we know x sub 2 is equal to 3 halves, that would be x sub 3 is equal to x sub 2 minus f of x sub 2 over f prime of x sub 2. And you could see, even with a simple function, how this can get out of hand pretty quickly, because now I have to plug 3 halves in for x sub 2. All right, so in this case, it would be 3 halves minus, I have to evaluate my original function for 3 halves. So 9/4 minus 8/4, so 1/4 up top. And then 3 halves times 2, that's just going to be a 3. All right, so that's 3 halves minus 1/12. So we're looking at 18 twelfths minus 1/12, so 17 twelfths. That's our second iteration. We have to do 3 iterations, so we need 1 more. All right, so we're doing the same thing, but we're plugging in a 7/12 now, which is just glorious. So we have x sub 3, so now we'll get x sub 4 is equal to 17 twelfths minus, well, 17 sixths on the bottom, I'm just doubling it. On the top, 17 twelfths squared minus 2. And then calculation. This is the extent of the by hand stuff that they would ask you to do. $289? Minus 288 over 144 to give us a 2 over 17.6. So a quarter, I'm sorry, 1/44 up top. $17.6 on the bottom. Keep, change, flip. We're talking about 6 over 144 times 17. That's just wonderful. I could simplify a bit here, I guess. That's not what I had in mind. 372, okay, so 124th.
Would they put this on the calculator section? This type?
They would not.
Okay.
They would not. Yeah, that's why I'm unfortunately stuck doing it. So with a common denominator, I'd be multiplying by 2 and 17 to get the same, yeah. So really the same thing as 34, but I want to keep it separated so I can actually do the math. So 289 times 2 would be 578. Minus 1 over 17 times 12, so 17 times 24. All right, so that's fun also. 17 times 20 is 340 plus 68, so 408. That was just a complete shot. 3, 4, 7, 17, yeah, 68. 17 times 4 is 68, right? So 340 plus 68. All right, well, whatever. Hopefully it's right. Anyway, let me show you how to do it on the calculator, so at least in the early goings you can check your work. And the calculator approach will check this for us, so when it turns out that I screwed this up, it'll show up over here. So go to your Newt program. So hit the program key and select Newt. Alright, so pretty straightforward. Select Newt, run the program. It asks you for the function x squared minus 2. It asks you for the initial guess. Initial guess and initial seed mean the same thing. Alright, so if you see either of those terms, it means the same thing. So in this case, 1. So hit 1, and then hit enter. It automatically, when you hit enter, it gives you the first iteration. So the 1.5. Then the second iteration, which, yeah, that looks like it could be. And then hit enter again, you get the third iteration, which looks like roughly the square root of 2. That's definitely not the square root of 2. But again, this is the idea behind this is to come up with an approximation of the square root of 2. So if I were to continue going, so all I needed was 3 iterations. If I were to continue going, the calculator would perform the iterations much quicker than we could until it gets repeated values in consecutive iterations. Once it does that, then it'll say done because it has fleshed out what the correct answer is or the correct approximation is. All right? So if you were to solve this equation, because again, we're looking for the zeros, set it equal to 0, add 2 to both sides, take the square root, you're going to get radical 2 or negative radical 2. So we have a sense of what the answer ought to be, whether we do it algebraically or use the calculator in Newton's method. But if we need only the third iteration, this would be the correct answer, assuming I did it right. So let's just verify real quick. It's in the same neighborhood, so if I made a mistake, it's one of those slight mistakes. All right, so got us pretty much there. The benefit of this is exactly the same, good. So the benefit of this is that we're able to work with an approximation that's written in an exact form, which is a weird thing to think about, right? Because an approximation in and of itself, you would think would be some kind of decimal value, but the idea that we can come up with something that looks like an exact value, but it is truly an approximation. Like for example, give me a fraction that is an approximation for pi. Something over something, yes, very good.
3.14 over 1.
3.14 over 1, you got it. Or you could say 314 over 100, right? That's a possibility. But the famous one is 22 over 7, right? So that's an approximate value. So if you had something like, you know, a function whose solution is pi, for example, I mean, you could go even very simple, like f of x equals x minus pi. You know, maybe through this iterative process, you can come up with an exact representation of an approximate value. All right. So that's the general idea. Now, for the second example, when they get into the, you know, within a certain degree of accuracy, this is your license to use a calculator. All right. When they say perform a certain number of iterations, that's a different story. You got to do that by hand. All right? And it'll be clear when is when. But for this, for the second one, Newt, the program, find your Newt. 2x cubed plus x squared minus x plus 1. An initial guess, all right? They didn't give us one of those, all right? The thing about Newton's method is your initial guess is very important because it will dictate what solution you're gonna be dragged to. All right, so your initial guess, if there's only one solution, if there's only one zero to the function, the initial guess isn't really going to matter, unless it's undefined for some reason. All right, because if there's only one solution, eventually it's going to drag you to the correct solution. Now, if there's multiple solutions, what it's going to do is drag you to the solution closest to your initial guess. So if you have, let's say, a 5th degree polynomial where you could have upwards of 5 possible solutions, then you might get dragged to the same solution over and over again depending on your initial guess. All right? So when in doubt, choose a positive value for an initial guess, choose a negative value, and then sprinkle in a couple of arbitrary values. So I'll throw in like a 10, and then hit enter. And hit enter again, and keep hitting enter, and so on. All right. The drawback, or at least the issue behind this approach, is kind of weird. It says with 0.0001 accuracy. What that's telling us is that we want our answer to be within 1/10,000th of the correct answer. All right. You really don't get a sense of that until you get down to the correct answer. All right, so what we do is we look for no change in the 4th decimal place. Once you observe no change from iteration to iteration in the 4th decimal place, then you know that you have the accuracy that you're looking for. All right, so my initial guess was 10. I also need to state the number of iterations, which usually means that I either have to keep track of the number of iterations throughout the process, or I have to do the process a second time, which is not a big deal because you're not doing it by hand, bless you. So I have no change in the 4th decimal place, so my solution would be negative 1.233. I would round that to 8. Unfortunately, you can't scroll back.
Okay.
So you just got to keep going until it says done, or you could break the program by hitting on, so that'll interrupt it. Run the program again, just type in the stuff. It's, again, still better than doing it all out by hand, which I had to do, but so, like one problem on the entire test. Took forever. All right, so I'm just going to take note of how many iterations it took to get to that particular number. Negative, the first time we got to that negative 1.233, it was a 7. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, consists of 14 iterations. Now, for the problem prior, it was something that you could easily have figured out. And the 15th one is where you have the repeated value, where there's no change. So we go for the first instance where there is that accuracy. The first one you verify easily. The second one is a little bit of a different story because you would need to actually find the zeros of the function in order to determine how accurate this was. All right, but once you start seeing no change in consecutive values or minimal change in consecutive values, you know that you're closing in on the final answer. All right, and that's really what we're looking for. There's more applications of this. We'll transition to a concept called differentials, and then from there to differential equations, which is the beginnings of antiderivatives, which I think is the fun part.